Earth system has so-called climate refugia. We have looked at this before. Around Galapagos, for example, there are certain corners where there is warming happening and the winds are changing, but somehow the topography, the islands produce upwelling, which help produce photosynthesis, phytoplankton, and the number of penguins grows there instead of decreasing, even with all this chaos going around. So this study reports that there are some climate refugia in the Great Barrier Reef as well, and we'll look at briefly again the processes by which these refugia may be getting created and see whether they have a hope of somehow helping the Great Barrier Reef well into the future. So it says climate refugia in the Great Barrier Reef may endure into the future. So they have found them with observations, they have done modeling for the future, and they think with the way climate change is expected to go, these climate refugia may persist into the future, which means at least the Great Barrier Reef in that region will benefit from that. So although global warming is leading to more frequent mass coral bleaching events worldwide, parts of the Great Barrier Reef have consistently escaped severe coral bleaching. Modeling and satellite observations show that climate refugia are created by the upwelling of cooler water to the surface through the interactions of tides and currents with dense reef structures. Here we use a high-resolution nested regional ocean model to investigate the future status of two relatively large refugia. On the basis of model projections under a high emission scenario, we can find that the upwelling mechanisms will stay active in a warming climate, and these regions are likely to remain approximately more than 1 degree C cooler than the surrounding waters until at least into the 2080s, providing thermal relief to corals. Identification and protection of these refugia may help facilitate reef survival and related biodiversity preservation by allowing their corals time to acclimatize and adapt, and ultimately provide source populations to replenish the rest of the reef. So reefs can grow, sprout, and then grow into other regions which are not protected by the refugia. We have discussed corals also, that there are some that are responding better than others, and they are finding ways to attach themselves to high temperature tolerant symbiont algae to survive, and so on and so forth. Okay, so it remains a complicated issue, but refugia are a common feature that happen even during an El Nino. For example, in the Eastern Pacific, when everything warms, refugia form where anchovies and so on can survive. Then what are they? Even during the most extensive global bleaching events, some regions have consistently escaped severe coral bleaching, suggesting that they could be climate refugia. Climate refugia for coral reefs refer to specific geographic locations that retain favorable environmental conditions for corals even when the surrounding areas experience inhospitably elevated temperatures due to the effects of climate change. Mesoscale eddies can also affect warming patterns, but large-scale patterns are usually not resolved by local scale patterns are usually not resolved by climate models. These local processes, such as upwelling induced by wind, currents, and tides, can create and maintain thermal refugia by moving cooler water from the depth towards the surface. However, these processes are usually not resolved by climate models, which have a typical resolution of around 100 kilometers, so they give you an indicator of what ecosystem impacts will be for the future and may be misleading in this context. Furthermore, climate models do not resolve fine-scale topography, either associated with small islands and coral atolls, which can mitigate the surface warming by interacting with the currents and tides to facilitate upwelling and enhance vertical mixing, so bring colder waters to the surface to damp the warming or even cool against a warming background. For example, enhanced upwelling associated with future strengthening of the equatorial undercurrent, which is a current that runs from west to east below the surface, is found to mitigate surface warming around several equatorial Pacific islands and atolls providing crucial refuges for marine biodiversity, but climate models did not resolve these topographic features and failed to identify such refugia. Refugia are the upwelling locations, I'm jumping ahead, where the hourly anomaly SST values averaged over the warm season are lower than -1 degree C. This approach of identifying upwelling locations using SST anomalies over a longitudinal transect from the coast to open ocean at each latitude, okay, along longitudes along each latitude, has been used to previously identify cool SST fronts with satellite observations. The 1 degree C threshold is also the basis for the common definition of cumulative heat stress used in the context of coral bleaching, such as a degree heating week DHW, which is based on number of days with SST more than 1 degree C above the maximum monthly mean over the previous 3 months, for example. Because the shelf break is oriented mostly along the north-south direction in the Great Barrier Reef, we use the temperature anomalies relative to the same latitude to highlight the role of shelf break and the outer reef topography on the impact of surface temperatures due to tidal pumping. By removing the mean temperature along the longitudinal transect from the coast out to the open ocean at 200 km past the continental shelf break, we capture the areas that are cooler than in both inshore and offshore waters. Basically, they have a methodology to argue that these are the refugia based on observations, and then you find corals there doing better than the warm exposed corals as well. So here are some details. You can see these streams of fronts of cold water among all the warmer waters, which are very specific to these regions, and there are some circulation patterns that matter. There are of course eddies and so on as well. So East Australia current here, New Guinea coastal current, and South Equatorial current here. The GPC is one of the cold eddies, I suspect. It will be here that I forgot already what it is. Sorry, Gulf of Papua current GPC is a little gyre here. It's not an eddy, and so on. So I won't go into the details, but you can see how warm waters are streaming down here and cold waters are stuck in between the warm onshore and offshore waters, which is what we mentioned before. Okay, here is the spatial extent and reef level prevalence of shallow water, which is less than 6 meters coral bleaching during 6 consecutive mass bleaching events on the Great Barrier Reef. So 98 was an El Nino, end of the El Nino, that had massive coral bleaching, but you can see these are the spatial extent and reef level prevalence of shallow water. So you can see the SST anomalies, and remember 1 degree C is a threshold for considering coral bleaching. So warm spots, cold spots, 2002 similar, 2016 behaved differently, obviously. 2015-16 was also a warm event. So various other factors may be playing a role as well. So 2017, 20 and 22. And you can see how mixed up the local scale warm and cold anomalies are, which is what makes them refugia, and which is what means that coarse resolution models cannot capture them. So you will need to do something like these people do with a high resolution regional model to look at what's happening in terms of processes and what will happen in the future. You know, they take projections from global models, use the winds, etc., to force a local model to do these things. There are uncertainties in the projections, but the processes will still show you, given those projections, what refugia might do. Okay, so here is the schematic representation of the tidal driven upwelling over a tidal cycle in the far northern Great Barrier Reef region, and satellite images showing densely packed reefs in the northern and southern Great Barrier Reef. So these are satellite images of the densely packed reef structures in the northern GBR and the Torres Strait. Okay, I won't go into the details there, but that's the region we already looked at here. Okay, you can see here different examples, and these are the temperature ranges going from 26 degree or lower to 32 degrees centigrade or higher, which is obviously too warm for the corals. So here is shallow water warms from solar radiation in the surface, and the Papua current that we talked about moves northward. Thermocline near coast below 100-meter depth is depressed due to geostrophy. So basically, depending on which way the current is going and which way the pressure gradient and the rotational forces are balancing, you get a response. You can see the expanded region here of warm water is stuck to the surface, is getting heated, and you have cooler water being mixed up and so on. This is the current that we saw before, the what did we call it? Gulf of Papua current. Sorry, Gulf of Papua current. Okay. And here flood tide then draws up water from below the thermocline that is channeled through the narrow reef passages onto the shelf. So very nice upwelling happening here. Cold water is mixed upward on the shelf from turbulence generated from bottom friction and from the surface downward from the wind stress. So there's turbulent kinetic energy which is mixing down, and bottom friction is mixing up. So you have very nice mixing of cold waters to create this refugia. As the tide ebbs, the cooler water remains trapped in the shelf among the coral reefs. So coral reefs provide this dense structure. Once the water comes in, it doesn't flow out as easily. Okay. This is the large-scale pattern and change in SST, sea surface salinity, and mixed layer depths, the well-mixed layer near the surface. And salinity and temperature are both important for the corals to do their business. Basically there are symbiont algae which have to survive, and all the fish that feed on them and provide services for the coral in terms of removing the CO2, providing oxygen and food and so on and so forth. Okay, so these are basically ranges. The data presented for two 20-year periods in the present day climate, so 1986 to 2005, and future climate 2080 to 2099. We are looking at SST, sea surface salinity, and mixed layer depth. And here is 1986 to 2005 temperature, salinity for the same period, and mixed layer depths. And as you go into the future, the long period 2080 to 2099, how reliable are these? Well, you have to be very careful, but nonetheless, just in this purpose, you can see that despite all the global warming expected, this remains relatively in the similar range. Let's say slight bit of warming, but you get the sea surface salinity, freshwater intrusions seem to be happening here, but the mixed layer depth remains shallow as well, which supports the SSTs to remain in this range near in the refugia. Okay, so you can see this has gotten warmer, this has remained somewhat closer. SST change is much lower here compared to all these regions. So is that good? Surface salinity change and mixed layer depth change. Obviously they are saying the refugia persist, which means this is still in a beneficial range for protecting the corals in those regions into the outer years near the end of this century. So this is looking at changes in strength of the ocean currents and SCC bifurcation location in the future. I won't go into this because I think the uncertainties at these such details are going to be quite large, because we are relying on large scale warming and wind changes and precipitation changes as well for salinities, and they are significantly uncertain, and they are taking one scenario of high emissions from all the different scenarios that the CMIP6 produces, the shared socioeconomic pathways based on various assumptions. And we know that the uncertainties in the projections are related to models and the internal variability for the first 2 decades, but at 2080 to 99 they are basically entirely related to scenarios and what assumptions you make. But in this context, you just want to know, given all that, will the refugia still survive? And the conclusion is that yes, they will. So here is again summertime decadal mean SST and latitudinal SST anomalies showing the warming patterns in the Great Barrier Reef and persistence of upwelling in the refugia areas. So this is the average for the 2050s and 80s. So this is SSTs in total going from about 26 to 32, and these are the anomalies, and again negative to positive. So you can see there are still blotches of cold temperatures, which means refugias will continue to function. Let's briefly read the discussion. The main point I want you to take out of this is that refugia are real, they are occurring in the historic period, so they are not made up. Then you want to see how long they will persist into the future with all the global warming going on. Optimistic message here is that they will survive into the future according to this model study. Using a regional ocean model that resolves tides and local topography, we have identified two large contemporary climate refugia in the northern and southern Great Barrier Reef, demonstrating the importance of local processes in characterizing climate refugia to inform climate-smart spatial planning to conserve biodiversity. There are risks, so resources are limited, and based on the risk profiles, you are going to take some action. The more information you have, the better, and the better knowledge of the uncertainty you have, it's going to be more helpful for optimizing resources as well. Reef scale oceanographic processes, especially the interaction of complex reef topography with tides and the channeling of currents through dense reef structures, are primarily responsible for localized upwelling events in the refugia. And remember that for assuming that the tide current reef interactions are going to be similar, you're assuming that the reefs are going to survive out to 2080 to 2099, because you are relying on those structures to produce the interactions as well. That's a big assumption there. In contrast, in the central GBR, while deeper cold waters intrude into the continental shelf during austral summer, they usually do not reach the surface, and the upwelling intrusion often corresponds to surface warming due to small tidal currents and less dense reef structures. Satellite observations and aerial reef surveys of coral bleaching over the past 6 bleaching events broadly confirm the existence of climate refugia identified by our models. So basically they are trying to understand the processes for observed refugia or observed bleaching events in some regions. Using the same regional model nested inside a 10-kilometer resolution near global model, we show that climate refugia could persist at least into the 2080s under the high emission scenario RCP 8.5, with surface waters in these areas continuing to be more than 1 degree C cooler than surrounding waters, providing thermal relief to corals in those areas. So RCP 8.5 is the business as usual, or the worst case scenario where we do nothing, which means this is the absolute worst case, hopefully. But anything else is going to be better, hopefully, right? These results likely represent a worst case scenario, as they are derived under the high emission scenario RCP 8.5, which now looks unlikely to be realized due to global climate actions. Coral reefs inside climate refugia could potentially provide source populations to replenish the rest of the reef, which should motivate renewed efforts to protect them. Okay, so don't give up on the Great Barrier Reefs. Rely on Mother Nature working with us with these climate refugia to help us protect them, provided we do our part. It's crucial that major reef restoration initiatives prioritize these refugia, as they are likely to continue to be the most favorable locations for sustained coral growth and health. I have jumped to the last paragraph. The protection of these potentially high-value refugia sites offers the best opportunity for natural adaptation and effective interventions to ensure the future security of the reef. Both southern and northern refugia will need to be fully protected. For example, although some reefs within the refugia are located inside the GBR Marine Park, but not all of them are fully protected. 17% of the refugia are for general use, 20% are for habitat protection, and 63% are classified as marine national parks. So there is a supplementary figure. You can look up what that all means and how these can change based on these Refugia studies. A substantial portion of the Refugia in the eastern Torres Strait is outside the GBR main park boundary and managed by the Torres Strait Regional Authority. We recommend that these high-value climate refugia be designated as high-priority protected areas to maximize success for natural adaptation and potential deployment of large-scale human interventions, such as assisted colonization of the coral polyps, assisted evolution of their survival into the warmer climates, and cloud brightening, which is expected to be a geoengineering experiment to reduce the warming over these regions, noting that robust global climate action is the only solution to limit the frequency and severity of exposure to heat stress. Given all this, there are many issues. For example, what would worry me is, with the warming everywhere, will the refugia be affected by the disease pressure that may end up growing over warmer waters? So many issues, but let's take the optimistic message out of this, that nature is doing its thing and providing some climate refugia which may help us better manage the survival of the Great Barrier Reef. Okay, see you in the next topic.